Hi, this is John Whitaker for the graduate level probability class, and this is our 11th video lecture. And today we want to continue further in our exploration of the relationship between random variables. We're going to start by looking at jointly continuous random variables and finding a CDF for the joint CDF for those two random variables in the continuous case through this example. And then we'll also talk about properties based on the joint CDF. We'll talk about expected value of a function of two random variables. And so let's go ahead and get started. So as an example, so today we'll start with an example. We'll let f of x comma y be equal to 5/16 x times y squared if 0 is less than x is less than y is less than 2, and 0 otherwise. P, the joint probability density function of x and y. And so the question will be, or the direction will be, in this example, to find the joint CDF of x and y, and that is f of AB. Okay. So again, if we remember, f of AB, what that's equal to is the probability that x is less than or equal to A and y is less than or equal to B. And that's equal, let me write this underneath. That's equal to the interval from minus infinity to B minus infinity A little f of x comma y dx dy. That's what we have for the continuous cases. Because of our integration area for which the joint PDF is non-zero, you'll remember this example. Here's the area of interest that we'll really be integrating over. It's pretty clear that if A is less than 0 or B is less than 0, then the probability that x is less than or equal to A or y is less than or equal to B, that's going to be 0. So we're going to start there. So in case 1, if A is less than 0 or B is less than 0, then we can say that f of AB is going to be equal to 0. For the probability that x would be less than some negative number, or y would be less than some negative number, and y will be less than some negative number, that's going to be 0 because you'd be integrating the 0 part of the joint PDF. So here's case 2. And again, I'll work on A as my kind of guiding variable here. So if A is sandwiched in between 0 and 2, then we have some subcases. So subcase 1, if B is sandwiched in between, turns out, between 0 and A. So the reason we break that up is because of this type of diagram. So I've got this picture, I'm going to reproduce it. Okay, so here's A. So you got that x is less than A, and you want y to be less than B. And what I'm thinking is if this is A right here, and this would be A here, and B is lower than it, it forms this picture, this triangle here that we integrate over. As opposed to if B was above A, we have this type of trapezoid shape that we have to be describing, and then we have a different description in terms of the order, in terms of the limits of integration. So this is one way to say I need to consider this subcase based on what the picture would look like that would yield the region of integration. So here, what we have is the integral. So f of AB would be equal to the integral. So it'd be from minus infinity to b. And then for each one of those b's, what did for each one of those y's, what did the x values run from? They run from 0 to y. And then we're integrating the non-zero part of f of x here. So that's 5/16 x y squared dx dy. That's what we're integrating. So for this part. And so here we're integrating with respect to x. So I have an integral from minus infinity to b. Here, an antiderivative with respect to x is 5/16 x squared over 2 y squared. We need to evaluate that as x runs from 0 to y. And then whatever we get for that, we need to integrate with respect to y. When I let x be equal to y, we end up getting integral from minus infinity to b. This will be 5/16. It will be y, no, it will be 5/32. Y to the fourth. And when we stick in 0, we subtract 0. So I'm not going to write that down, dy. I said minus infinity to b. That's correct, but really it's not. It should be 0 with me already having substituted the non-zero part for the PDF, the joint PDF. So this should be 0, so I made a mistake. Let's finish it right here. Antiderivative for this guy is 5/32. Then it will be y to the fifth over 5, evaluate from 0 to b. Those are the y values. So the 5's cancel. We're left with 1/32. When I stick in b for y, I get b to the fifth. When I minus what I get when I stick in y to 0, but I just get 0 there. And so that's the answer in this region. Okay, we're going to have another subcase, and that's where the b was bigger than the a, yet less than 2. So subcase 2, remember a is sandwiched in between 0 and 2. So here we have b is bigger than a, but yet still less than 2. And so our picture in this case looks like the following. So maybe here's a. And here's, this is still a along the y-axis. Let's say b is up here. And so that's the region which I'm going to be integrating. So here, in this case, f of ab is that region over which we're going to integrate. How do I describe this region? In this case, it's much easier to switch the order of integration. Here's the reason. If I integrate with respect to x, then y. So we'd be fixing a y. For this particular y value, the x values would run from 0 to this line. For this particular y value, the x values run from 0 to a different line. So I'd have to split up this double integral into 2 different double integrals to represent this region, where b is bigger than a, and the region for the y values that are less than b. When y values are bigger than a, we have different regions. So I'm going to integrate with respect to y first, then x. When I do that, we say, well, what do the x values run from? The x values run from 0 to a. For each one of these x values, what do the y values run from? They run from this line. So I'm talking about the y values. That's the y of x. They run from x up to this line, which is b. That's what we have. All right, and so what are we integrating? We're integrating 5/16 x y squared. 1. Once you do that, that's what we get. So with respect to y, I have 5, so it's the integral from 0 to a. 5 is, with respect to y, the antiderivative of y cubed over 3, so this becomes a 48. X, y cubed, evaluated as y runs from x to y runs from b, dx. So when I stick in y equal to b, I get integral from 0 to a of 5/48. This would be b cubed x minus what I get when I stick in for y equal to x, that's 5/48. Would be x to the 4th dx. When I integrate with respect to x now, what I'm going to get is 5 out of 96 b cubed x squared. It should be x squared over 2, but I put the 2's in the bottom already with the 48, and we'll probably get that together. Minus, here this would be 5 over 48, x to the 5th over 5. I need to evaluate that as x that runs from 0 to a. When you stick in a, here's what you get. You get 5 over 96 b cubed a squared. Minus, the 5's here will cancel, so I'm going to rewrite this as 1 over 48 a to the 5th. When I stick in 0 for x, I'm going to have subtraction 0, so that's what I get for the joint CDF in this situation. Okay. The last subcase we have is when b is greater than or equal to 2. So here's what we're looking at. Okay. So a is something like this. X has got to be less than a. B is up here. And so we're just looking at, f of x comma y, the joint PDF, over this region. And this region, over this region, part of the time, lots of the time, the joint PDF is 0. The only part where it's not 0 is right here. This becomes what I'm going to integrate. So I'm going to rewrite this as big F of AB is equal to the integral, double integral, and I'm going to integrate again with respect to y first. So x last. We're going to have 5/16 xy squared. And the x values run from 0 to a. For each x value, the y values will run from x up to b. That's what they run from. So that x value, the y value run from x to b. But b here, I'm sorry, it's not b. It's 2. X to 2. And so that's what we got to compute. Okay, so then go from 0 to a. Here I find antiderivative with respect to, I wrote this incorrectly, this is dy with respect to y. So again, we're going to do 5 over 48 xy cubed, evaluated from x to 2, whatever we get, dx. Integrate with respect to dx. This is the integral from 0 to a. You stick in y equal to 2. This is going to be 5 over, well, when y is 2, we get 8. 8 goes into 48 6 times. So it's 5 6 x, okay, minus, when I let y be x, we're going to get 5 over 48. This is x to the 4th. And then we need to integrate with respect to x. This is equal to 5/12 x squared minus, it would be 148 x to the 5th, evaluated from 0 to a. So here I get 5/12 a squared minus 148 a to the 5th, and when we stick in 0, we get nothing. And that's the correct answer. Okay, all this was based on where A was. In this case, A was sandwiched in between 0 and 2. Well, what if A is bigger than 2? This is the third case. Case 3. A is bigger than 2. Now, if A is bigger than 2, we're going to have subcases again. So here's subcase 1. It's where B is sandwiched in between uh, 0 and 2. Okay, so here's our picture. A is over here. We know that we're talking about the x being less than this. And so here, the only thing we've got to worry about is where is B. We know it's between, it's bigger than 0. We've already handled the case where B is less than 0. And so here, what if we're looking at something in here? So the only reason we integrate over is just a small triangle. So how do I describe it? Well, I'm going to do dx dy. I can do that this time very easily. 5/16 x y squared. Again, I'm only integrating over the part where the joint PDF is non-zero. So for this, the y values run from 0 to b, and for each one of those y values, the x values will run from 0 to this line, which is 0 to y. Okay, when I integrate this, so this is what f of a, b is in this situation. When I integrate this, it's 5. So integral from 0 to b, still to be done. It's 5, I'm integrating with respect to x. It's 5 over 32, x squared y squared, evaluated from 0 to y, dy, which is equal to, when I let x be equal to y, we get 5, so I've got an integral from 0 to b, 5 over 32, this will be y to the 4th, and I subtract, when x is 0, I just get 0, so I'm going to leave that as is, dy. That's equal to, so I integrate with respect to y, it's 5 over 32, y to the 5th over 5, evaluated from 0 to b. The 5's cancel, we're left with b to the 5th over 32. That's what I think I get. That's correct. There's one more case to consider. So last subcase. That's when b is bigger than or equal to 2. And so in this picture, what we're looking at is this scenario. So A is over here, B is over here. You're saying, what's the chance that X is in this area, X and Y are in this area? And so for that to happen, really, this is the only non-zero part of the joint PDF, and we get to integrate over all of it. So this ends up being f of a, b is equal to the integral. And so this would be from 0 to, I'm going to do it with respect to y last, so it's dx. So for each one of these y's, the x values run from 0 to y, the x values do. And again, it's 5/16 xy squared. Okay, we integrate this with respect to x. We get 5/32 x squared, y squared. We still need to do an integral from 0 to 2. And we first need to evaluate this from 0 to y. The x values are running from there. And then once we do that, we integrate with respect to y. So here, this integral from 0 to 2, I let x be y, I get 5/32, y to the 4th. When I let x be 0, I get nothing, dy. That's equal to 5 over 32 times y to the 5th over 5, that way from 0 to 2. 5's cancels, 1 over 32, 2 to the 5th, and that, of course, equals to 1. Having done all that, let me summarize the definition of what the joint CDF is. And this case, in this example. Okay, so, for our example, f of AB is equal to, here's what it is 0 if A is less than 0 and B is less than 0. It's equal to B to the 5th over 32 if 0 is less than or equal to A is less than 2 and 0 is less than or equal to B is less than A. It's 596b cubed A squared minus A to the 5th over, I think it's 48. If 0 is less than or equal to A is less than 2 and A is less than B is less than 2. It was 5/12 A squared minus A to the 5th over 48. If, here we had 0 is less than or equal to A, less than 2, and we had that B was greater than or equal to 2. We have B to the 5th over 32 again. If A is greater than or equal to 2, and 0 is less than or equal to B is less than 2, and finally we get 1 if A is greater than 2 and B is greater than 2. B is greater than or equal to 2. So that's our summary for the joint CDF for this particular example. A lot of work there. A lot of calculus involved in terms of the double integrals, so Cal 2. Okay. You know, with the joint PDS and PMS, we worked with trying to find individual PMF or PDF. And we can do that for the CDS. So here's a fact. Let F of A comma B be the joint CDF of X and Y. Okay. All right. Then the CDF of, so we have two results here, of X is big F sub X of A, and what it's equal to is F of A infinity. And 2, Y is F sub Y of B, and what is that? That's F of infinity B. So we think of this as this extended real value function where we can stick in infinity or minus infinity. So that's what we have, and the proofs of these are very easy. So for one, here's what we think of. So what F sub X of A is, remember that's the probability that X is less than or equal to A. And that's the same thing as the probability that X is less than or equal to A, and Y is an element of real numbers, meaning it's less than or equal to infinity. And so on both those things happening, X is less than or equal to A. All right, and that's just equal to, I have room over here, that's nothing more than F of the joint, F of A, comma, infinity. Similarly, for 2, it's the same type of work. F sub Y of A is equal to the probability that Y is, not A, it's called B, is Y is less than or equal to B. That's the same thing as probability that X is less than or equal to infinity. So we don't care what's happening with X. And Y is less than or equal to B. But that's the same thing as F of infinity B. that's the end of the proof that we need to do that. Okay. So here's something analogous to what we've seen before. And it's a fact. So it says, let x and y be jointly contiguous then the set partial derivatives, derivative with respect to A, derivative with respect to B, of f of AB, where we're thinking that this is the joint CDF, is equal to the joint PDF. So here's the proof. So if we're taking the partial with respect to A, partial with respect to B, so we do B first, of the joint CDF. What's that equal to? So let's just rewrite this. This is partial with respect to A, second, partial with respect to B. And then what is this? This is nothing more than the integral from minus infinity to B, integral from minus infinity to A, of the joint PDF, f of x comma y, and then this would be dx dy. So that's what this is. I'm going to switch the order of integration in a second. So this is derivative with respect to A, and then I'm going to rewrite this as the derivative, I'll do it right now, with respect to D, and I'll switch the order of integration and rewrite this as the integral from minus infinity to A, integral from minus infinity to B, f of x comma y, dx dy. Sorry, dy dx. We do this first partial derivative. With respect to A, that plays no factor. We can pull that partial derivative inside that integral. It's an integral from minus infinity to A of the partial with respect to B of the integral from minus infinity to B f of x comma y dy dx. Now, this partial derivative of this function, where we're just integrating with respect to y, and so if you will, I'm going to think of this as an iterated integral, and so we're just doing the partial derivative, just this part. Okay? And with that being what's occurring, here, this partial derivative, using the fundamental theorem of calculus, it becomes, so this is the derivative with respect to A, of integral from minus infinity to A, and now this part, using the fundamental theorem of calculus, becomes f of x, and we just stick in B. So that's what happens to that integral. Dx. And again, we use the fundamental theorem of calculus. And so we get the result. I'll write it on this board. So that partial derivative, that integral, they undo each other, if you will. You just get f of A, B. That's on the calculus. That's what it is. Okay. Here's a definition. So let x and y be random variables. Either both discrete or both continuous. Let g of x comma y be a function expected value of g of x comma y is, so it's denoted by e of g of x comma y and given by, so it depends on the scenario here. It's one of two things. It's either the sum over the x's, sum over y of little g of x comma y, f of x comma y, where f of x comma y is the joint PMF here. And this is if x, y are discrete. And here it's the double integral, so it's from minus infinity to infinity, minus infinity to infinity of g of x comma y, f of x comma y, dx dy, if x and y are continuous. And so I'm not writing that out, that the little f of x comma y is the joint PMF or joint PDF in respective cases, but that's what it is. Okay, let us look at an example. So let's look at something we're familiar with. Let's let f of x comma y equal to x plus y equal to 21. Excuse me. Where x is equal to 1 and 2, and y is equal to 1, 2, and 3. Be the joint PMF, probability mass function, for x and y. Okay, and then here's what we might be asked. Might be asked to find the expected value of x squared times y. Okay, well, I just do what's listed there, and so by the definition, this is the answer. The expected value of x squared times y, is equal to, it's a double sum. Here the x values run from 1 to 2. The second sum is y running from 1 to 3, in this case. It would be of x squared y times f of x comma y. Alright, so let's let x be 1. And so we do the sum, so we have 1. So here's what's equal. 1 times, and then y would be 1, so it's 1 squared f of 1. Plus 1, that's x. X is being squared, I'm sorry. So it's 1 squared times 1 times f of 1. Now it's going to be 1 squared times 2 times f of 1, 2. Plus, here it's going to be 1 again, so 1 squared times 3 times f of 1, 3. Plus, I got a little bit more, now x is 2. So it's going to be 2 squared times 1 times f of 2, 1. Plus, it's going to be 2 squared 2 times f of 2, 2. I got just enough room to say plus. It's going to be 2 squared times 3 times f of 2, 3. Okay, so now we need to put in numerical values for the joint PMF. Make the computation. Okay, what's that equal to? So let's see. This 1 times f of 1, 1 is 2 over 21. Plus, this 1 is going to be 2 times f of 1, so that's 6 over 21. Plus, this is 3 times 4, so that's 12 over 21. Plus, here's 4 times 3, that's 12 over 21. Plus, here's 4 times 4, that's 8. 8 times 4 is 32 over 21. Plus, 1, 2, 3, 1, 2, we're down to the last one. So that's 4, that's 12. 12 times 5 is 60 over 21. Let me do this. It's 92, 94, 104, 104, 106, 116, 22, 124. That's the answer I got. 124 over 21. That's the right answer. Let's do another example. So let's let, in the continuous case, f of x comma y equal to what we're familiar with, 5/16 xy squared if 0 is less than x is less than y is less than 2, and 0 otherwise. Be the joint PDF of x and y. Again, I'm going to have the same directions. I'm going to find the expected value of x squared times y. Okay, so the answer is, so the expected value of x squared times y, that's supposed to be minus infinity minus infinity to infinity of x squared y dx dy. Remember, this, made a mistake, times f of x comma y dx dy. Now look, f of x comma y is often equal to 0. When isn't it 0? Well, it's not 0 in this part of this square. So I won't describe that part, because otherwise we're just integrating 0, which would be 0. So here I'll say this is equal to n equals 0 to 2. That's what the y values run from. For each y value, the x values run from, on this path, the x values run from 0 to 1. X squared y, here this was 5/16 xy squared dx dy. Fantastic. This is equal to an interval from 0 to 2. Interval from 0 to y. Let's simplify this. So it's 5/16 x to the third, y to the third, dx dy. Integrating with respect to x first. So I get 5/16. Well, that's true. But when I integrate with respect to x, I'm going to get x to the fourth order. And so I need to divide by 16, but I'm also going to divide by 4, so let's just make this 64. X to the fourth, y to the third, need to evaluate that from 0 to y, still need to integrate with respect to y over the region from 0 to 2. This is equal to integral from 0 to 2. When I stick in y, I will get 5/64 y, I think, to the 7. When I let x be 0, I get nothing. And then dy. This ends up being an awful problem. So let's see, it's 5/64 y to the 8 over 8 evaluated from 0 to 2. Okay, maybe it's awful. So when I let x be 2, this is 2 to the 8. All right, so what is that? It's 5/64. This will be 2 to the 8 is 2 to the third times 2 to the fifth over 8. So I wrote it down this way because what's 2 to the third? It's 8, so this cancels. So I got 5 and 2 to the fifth. What's that? That's 32 over 64. Well, my goodness, that's just 5/2. That's really nice. Okay, so that's our answer. Okay. Now I want to look at some facts. So, at least one fact right now. The expected value of x plus y equals to the expected value of x plus the expected value of y. If both x and y are discrete or both are continuous. Let me prove that. So let's let x and y, so this is like case 1, be both discrete. Then the expected value of x plus y is equal to the sum of the x's, sum over the y's, of x plus 1, f of x, xy, that's the joint PMF, and that's what we have. So this ends up being the sum over the x's, the sum over the y's. If I distribute this, is x times f of x comma y plus y times f of x comma y. We'll break this up and get out of the way. We'll break this single double sum into 2 double sums now. Okay, so this is equal to sum over x's, sum over y's, of x, f of x comma y, plus sum over x's, sum over y's, of y, f of x comma y. I'm going to tell you about the definition. You can actually stop here by the definition of the expected value of g of x comma y. This is really the expected value of x. This is really the expected value of y. We're done. But I want to go a little bit more details than that. Really, that's true. What I want to tell you is that you can, if you want, you can pull out the x in this case. Plus, here we switch the order of summation. Can't always do that, but we can, in this case, provided the expected values are finite. Here we're going to have y, f of x comma y. I can now look at this second sum. If we sum up over the y values of the joint PMF, well, what that does, it just gives you the PMF of x plus, here I can pull out the y, sum over the x's of f of x comma y. That's equal to, here, if you take x times its PMF and sum that up, what you're getting is the expected value of x. Plus, here, this is the sum over the y's of y, but the sum over the x's of the joint PMF is nothing more than the PMF of y. And so, the expected value of x is there. This second part is nothing more than the expected value of y. So that's the proof when x and y are both discrete. The second part, when x x and y are both continuous. And it's similar. Suppose I say are both continuous, they're joint continuous. Then the expected value of x plus y is equal to this double sum from minus infinity to infinity, minus infinity to infinity, of x plus y, f of x comma y, dx dy. That's what it is by definition. Again, I'm going to write down this double integral and distribute the f of x comma y. You get x times f of x comma y plus y times f of x comma y, and then that's dx dy. That's equal to, we write down two integrals, I should say, two double integrals. This is x of f of x comma y dx dy plus, again, the double integral from minus infinity to infinity, minus infinity to infinity. Here is y f of x comma y dx dy. So this is analogous to what we just did with the summation. We're going to do the exact same thing. Again, I could, at this point, say, well, that's expected value of x plus expected value of y. I'm going to show a little bit more details this time. Well, that's equal to, so in the first one, we're integrating with respect to x first. So we'll switch the order of integration. So here's minus infinity to infinity, minus infinity to infinity. I'm going to write down x, f of x, comma y. I'm going to write down dy dx. You switch the order of integration in these cases. Integral from minus infinity, we're doing with respect to x first. So I pull out that y that was there. And now that integral from minus infinity to infinity, f of x comma y dx dy. Here I can pull out the x. Plus here, outer integral. The inner integral is the integral of the joint PDF with respect to x first. And that just gives you the PDF with respect to y. Still need integrate with respect to y. Here, similarly to what we just did, is it says the integral of the joint with respect to y is the PDF of x. Still need to integrate with respect to x. Plus, this part is y times its PDF. You want to integrate that over the whole real line. That is the expected value of y. This integral right here is the expected value of x. And you have plus the expected value of y, and that's what we wanted to show. So we're showing it in all possible cases. Next thing we'll look at is the concept of independentness for random variables. So here's the definition. Two random variables say x and y are said to be independent if for all subsets A and B of R, okay, the probability that X is an element of A and Y is an element of B is equal to the probability that x is an element of A times the probability that y is an element of B. That's its definition. An alternative definition here's what it says. It says two random variables x and y are independent if their joint probability, their joint CDF is equal to the product, their joint CDF is equal to the product of the individual CDFs. So f of AB is equal to f sub x of A times f sub y of B. That's alternative definition. Using those two definitions, we're going to prove the following if and only if fact. Here's my fact. It says x, two random variables, x and y. Are independent if and only if the joint PMF PDF is equal to the product of the individual PMFs and PDFs. So, okay, so here's the proof. We're going to run through this fairly quickly. We're going to go in this direction. So we're going to say, let x and y be two independent random variables. In the case we're going to prove for, or if both of them are continuous and both of them are discrete. Let's start with case one. Suppose x and y are discrete random variables. Discrete. We're going to use that original definition to get the result we want. Here's the way it goes. It says, so here, f of x comma y is equal to the probability that x is equal to x and y is equal to y, which equals to the probability that x is an element of x and y is an element of the set containing y. That's what we can write that. And because of an independence, that's probably that x is an element of the set containing little x. I didn't write down my little x very well here. Times the probability that y is an element of the set containing little y. And that's the same thing as the probability that x is equal to x times the probability that y is equal to y. And that's nothing more than f of x times f of x times f sub y of y. So that's what we wanted to prove. Case two, here x and y are continuous, jointly continuous. Okay, that's what we're thinking about. Then in this case, what we do is we notice that f of AB, so we use that alternative definition. This is equal to f sub x of A times f sub y of B. So, if we differentiate this with respect to A and B, that's the same thing as we've proven before. F of, well, it would be AB. Now, little f of AB. Also, if we consider these partials, derivatives, of f sub x of A times f sub y of B. So this will be a constant with respect to B, so what we get is equal to, well, let me write it a little slower. And so doing that partial with respect to B first, this is a constant, so this is equal to partial with respect to A of f sub x of A times the partial with respect to B of this, but that's just f of f sub y of B, and that's a constant with respect to A, and so when you take the partial with respect to A, you just get the partial with respect to A of the CDF of x, which is nothing more than the PDF of x, and so we get the desired result. So now we've got to go another direction. We're almost done. So for the other direction, we're assuming f of x comma y equals to f sub x of x, f sub y of y. And so we want to show independence of case 1. X and y are discrete. So you look at f of AB. In the discrete case, we have the sum over all x values less than or equal to A, sum over all y values less than or equal to B, of f of x comma y. But because we're our assumption, we can rewrite this sum over all x's less than or equal to A, sum over all y's less than B, of f of x times f sub y. And then we split those up into sums. So here I pull out the f sub x less than or equal to A, f of x of x, sum y less than or equal to B, f sub y, and that's equal to f sub x of x, or if you will, A, times f sub y of B. Finally, last result. Case 2, x and y are continuous, so we do something similar. We note the probability x is an element of A and y is an element of B is equal to the integral from B, integral over A, f of x, y, it would be dx dy. Here, because of our assumption, this B, this A, this will be product f of x times f sub y of y, dx dy. I pull out the dy, b f sub y of y, integral A f of x, dx dy. This integral is nothing more than m sub x, well, it's just the probability that x is an element of A, dy, and then that's a number, so we pull that out, times integral over B of f sub y of y, dy, and that's the probability of x is an element of A times the probability of x is an element of B. And therefore, that's what we want to show, that shows x and y are independent. So we looked at all possible cases and proven the results. Thank you very much for your time and patience.